So for the third and final part of this section on ForkJoinPool, we're going to go ahead and talk about some of the methods that are provided in ForkJoinPool and the related classes like ForkJoinTask. And I'm going to show you how to apply these things to do operations on big fractions. So it'll be yet another big fraction operation program, which you can see here. We'll walk through some of that code. So let's talk about some of the key methods in ForkJoinPool. As we said before, a ForkJoinPool extends the executor service. So as a result, it implements the common executor service methods like execute, a runnable, submit, a callable, invoke all, invoke any. You would very rarely use these methods because what's the point? You might as well use threadpool executor instead of ForkJoinPool. And the reason why you wouldn't do this is they don't leverage all the cool features that you get with a ForkJoinPool. Therefore, we have a bunch of other methods. So execute, invoke, and submit are kind of the way that you have non-ForkJoinTask clients submit work into the pool. And these, of course, leverage the powerful properties of the ForkJoinPool, which is why we want to use them. So what execute does is it arranges to asynchronously execute the ForkJoinTask, which will not return a result, so it just runs. This would be something you might do for some kind of server, for example, where you don't really need to get a return value. It'll send back something through a network connection or whatnot. Invoke is used to perform a task and then block until the task is complete. You can see you get a result back, which is whatever the task return is its return value. That's what I most commonly use for my examples. And then there's also a method called submit, which submits the ForkJoinTask to the pool for execution and returns a future. When you create a ForkJoinPool, by default, it will default to the number of cores available on the Java virtual machine. You can set it to be whatever you want here, but you're probably best set it to something that's reasonable, like the number of processors on the machine. But you can also control it. If you don't want it to use that many cores, you can limit it. The common ForkJoinPool can be accessed by a method called commonPool. It's a static method, so you just have to say ForkJoinPool.commonPool, and that will go ahead and return to you the common ForkJoinPool, which is actually allocated on demand. So the first time it comes in, it'll be created. And this common pool will be used by any ForkJoinTask that's not explicitly given to a specific pool. So if you don't explicitly submit something to an explicit pool or specified pool, it'll default to the common pool. There's also a bunch of interesting little helper methods that you can use to see what's going on under the hood, tell you what the target parallelism is, the size of the worker threads, how many things are queued up that have not yet started to run. You can find out how many threads have been stolen. These are not things you would typically use in a program, but the framework might use those things for some kind of debugging purpose. So let's talk about some of the methods in ForkJoinTask. So ForkJoinTask implements the future interface. So it's basically a very fancy kind of future. And you can therefore use it to asynchronously execute a task in either the current ForkJoinPool, or you can put it in the common pool. So you can kind of designate where it's going to go. So when you fork something, it's going to go ahead and it'll arrange to run this thing in the appropriate pool. That just means it queues it up in the right place in the deck that's part of that thread, the worker thread. And you can see that fork gives you back a ForkJoinTask, which is a future, so you can eventually wait on it. And the way you'll eventually wait on it is by joining. Fork pushes the task to the head of the deck in the current thread. So when you say fork, it pushes it onto the deck. Join will return the result of the computation when it's done. What it basically says is this task will not continue to execute until the forked subtask has completed. But as we talked about before, this is very clever in the way it works, and it doesn't actually block necessarily. It may actually use it may use the worker thread to do computation of other tasks until the task that it's being joined on has been completed. And then invoke is kind of fork followed by join. So this will go ahead and fork the task, and then it'll wait for it to finish. You may or may not need to use this. It to some extent, impedes asynchrony, right? Because it's going to block. So we don't typically want to block. All right. So let's talk about recursive tasks. Remember before I mentioned how we have ForkJoinTask, which you rarely directly program. But instead, there are these other subclasses, the recursive action, recursive task, counted completer. So let's take a look at recursive task. And recursive action is very much like recursive task. It just doesn't have a return value. So recursive task extends ForkJoinTask to return a result, which is type V, which is the value. And you have to override the compute method. So you can see compute is an abstract method which you have to fill in. And the way this is going to work is the compute that you write may actually split up this task into smaller subtasks, right? So it may recursively fork some more. So it's going to split it up into smaller pieces. And then compute will typically go off and do some stuff, and then when it's reached a point where it can make no more further progress, it will go ahead and join the results of the smaller subtasks into a collective result, right? So it splits it up, and then it joins it back together again in the future. And then there's also a method called exec, which is going to be called internally by the ForkJoinPool to cause the recursive task to do its computation and return the result. So you don't have to really think about exec. You don't have to implement it, but that's what's done for you under the hood. All right, so let's talk about how we could actually apply this thing in practice. And we're going to look at the example here, which is example 22. So this is example 22, and this example shows how to use the ForkJoin framework to do various operations on big fractions using the Java ForkJoinPool. So you can see here we're going to end up with, we're going to use 12, we're going to have 12 big fractions we're going to want to do stuff with. And we're going to go ahead and define ourselves a constant, which is going to be one of the things we'll do. We're going to make a big fraction with a big numerator and a big denominator that's been reduced. And then we create ourselves a completed future for this big fraction. We just need that later to make the whole thing work nicely. We go into the main program. We're going to create a list of random unreduced big fractions. And the way we do that is we generate a stream of big fractions randomly. We limit them to 12, which is the S max fractions value. And then we collect all those things into an array list. So now we've got a list of random big fractions that are unreduced. Here's the operation we're going to do. We're first going to take whatever big fraction we have randomly, and we're going to reduce it, and then we're going to go ahead and multiply it by the constant we showed before. So that's the operation there. And then we're going to run all the tests. And this is actually really cool. So I have this little helper class called runTimer. And you can pass in a lambda expression and a string, and it will go ahead and it'll run that particular test. And as you can see here, we're going to test 4 different operations: test fraction operations 1, test fraction operations 2, test fraction operations 3, and test fractions operations 4. And each of these things will do a slightly different way of processing the big fractions using completable futures. I'm sorry, using ForkJoinPool. And then when we're done, we go ahead and get the results, and we'll print them out. Now, let me go ahead and run this for you just so you can see what it does. So if we run this thing, and unfortunately, this window is rather small, but when we run it, you can see it spends a fair amount of time doing all the computations because the numbers are large and multiplying big fractions is a non-trivial thing to do. And when it's done, it prints out the results. You probably can't read them very well. Let's see. See if there's a way to, I guess you can't easily expand the window size. Anyway, this said that the implementation number 4 ran the fastest and implementation 1 ran the slowest. And we'll take a look at the code and you'll see what they do here in a second. Okay, so let's go take a quick look. Here's how we make ourselves a big random fraction. So we make a big integer with some gigantic value, and it's random. And then we make a denominator that's going to be used to divide that. And then we make ourselves a reduced big fraction. So that's just getting ourselves the data to work on. And here are the 4 operations we're going to look at. So the first one is going to take this list of big fractions, and the operation to perform is a function lambda. And it's going to call apply all iter. on the common pool. So you can see it passes in the common pool up there. And every one of these things works the same. Basically, they pass in the fraction list, the operation, and the pool to work on. And then they are each going to do different things to do the processing with the fork join pool in a slightly different way. So this one's going to go ahead and apply the apply all iter method, and we'll look at that in a second. This runs the invoke all method. This runs the apply all split implementation method. And then the last one we have is apply all split index. These 4 method calls were helper methods that I implemented, and they appear over here in this class. So these are the fork join utils, and it's a utility class that we make a private constructor just so that we aren't tempted to make an instance of this thing, and everything's called through methods. So let's take a look at apply all iter first. What this thing's going to do is it's going to take a list of type t, which in our case is big integer. It's going to take a function to apply on each element in the list, and it takes a fork join pool in which to do the processing. So you can see here we say ForkJoinPool.invoke. Remember, invoke is the method that's going to submit a fork join task and then block until it's done, and it'll return the result. And what we're going to do here is we're going to make ourselves a new recursive task with a compute method. Now again, sadly, we cannot use lambdas here. It would make it a little bit less syntactically dense, but we're defining a compute method for an anonymous instance of recursive task that's parameterized with a list of t. So here's what compute is going to do. Compute is going to create a linked list to hold all the forked tasks. So we have a list of fork join tasks. We're going to create a list to hold the results of all the joined results. So this is the thing that's going to be forked. These are going to be the results when we join them. And then we're going to iterate using, we're mostly here just using Java 7 features. I decided not to use any Java 8 stuff just to keep in the spirit of the fork join pool. If you use Java 8 stuff here, it's even cooler, but I want to just use Java 7 stuff because this is kind of a Java 7-esque feature. So we're going to iterate through every element in the list, and for each element, we're going to go ahead and add a new recursive task to our forks list, right? So we're going to add a new task to this list. And this task is going to have a compute method, and that is going to go ahead and apply the operation to the value t, right? So this is the list of big functions, big fractions, and we're going to apply the operation to every element in that list. Okay, so that's what that's doing. And notice that what we do here is we're adding a new recursive task that we've forked. So we're going to say fork. So for every element in the list, we're going to fork a new task, and we're going to add the forked task to the list. So remember, when fork is called on a task, it arranges to run it in the fork join pool. And what this will do is, because of the way we've designed this, this will always be calling fork in a given thread, and it'll go into that thread's deck, and then the other threads in the pool will steal the deck. It'll steal the tasks from that deck. So we go ahead and we add all these things in. So at this point, we've got, n elements, one for every element in the list, all running in parallel. And then we come down here, right? So after we've forked them all off, they're all off doing their thing. We then come down and we say, for every element we've forked, give me a task, and I want to join the result and add the joined result to the results list. So this is remember, this join call doesn't block per se. It will simply work in conjunction with the pool of threads to essentially do computations till that task that join was called on is completed, in which case it'll return the result, which will get added to the results list. So by the time this loop finishes, all the results have been joined into this list, and then we go ahead and return the list of results here. So this is basically going through the list, from left to right, and forking everything off, and then joining everything at the end. So it's essentially an iterative way of starting up all the processing in the pool. Okay, so that's that one. Any questions about that? Here's invoke all. Invoke all is kind of funny. What it does is it goes ahead and it makes a list of callables, and it goes ahead and it adds each operation in the list of callables a lambda expression that's going to apply the operation to the big fraction. Every element in the list is going to be, we're going to create a callable that will be stuck into this list of callables. And then we're going to say ForkJoinPool invoke all. And invoke all is a method that goes off and invokes all the callables in the collection, and it returns a list of futures to the results. But oddly enough, they have already completed by the time invoke all returns. Since we got back a list of futures, we have to convert that list of futures to a stream. Then we go ahead and get each of the elements, and we turn that back into a list of completed results. So this is basically using a mechanism built into the ForkJoinPool to run a collection of callables all at once, if you will, which actually does something that looks quite a bit like what I show you right here. So it's doing pretty much the same thing. All right, we got two more things to look at. One is called apply all split. And what apply all split does is that goes ahead and will recursively split the list up and run each half as a sublist in the ForkJoinPool, and it'll do this recursively. So you'll see we define something called a splitter task, which I'll show you in a second. And what we do here is we say ForkJoinPool invoke new splitter task, and we pass in the original list as the initial list. And then you see ForkJoin, the splitter task is going to have a sublist. It's going to have a variable it's going to use to keep track of a portion of the list, the sublist. Its constructor simply assigns what it is given to that field. And then here's the compute method. So what compute does is it says, is the list less than or equal to 1? If so, we'll make a result list, and we'll go through and apply the operation to every element, which typically is just 1, right? So we're going to apply one thing, and then we return the result list, which has a subset of the results. Otherwise, what we do is we figure out the midpoint of the list by taking its size and dividing by 2, and then we go ahead and we make a new splitter task that takes the left half of the list, and we fork that off. We go ahead and modify the sublist to take the right-hand side of the list. So we split the list in half, so we have the left half and the right half. We then compute the right half, and then and that will run in parallel to the thing that's been forked. So we fork it off, and then we run ourselves on the right half. We get the right results. We join the left task to get the left results, and then we add the right results to the left results, and we return the left results. So this is a classic sort of divide and conquer approach using the ForkJoinPool. So we split things up evenly into chunks. So that's one approach. And then let me show you the very last approach. This is my favorite approach because it's so cool. Sometimes it works better, sometimes it doesn't. Each of these things has their own pros and cons. This approach, notice that the approach we just looked at divided the list in half, right? So it split it in half. This approach keeps everything in one place, and it only has a splitter that keeps track of the indices in the list. So it doesn't actually make a copy of anything. It just keeps track of the indices. So what we have to do, and this is completely insane reflection-like approaches, we are going to create ourselves a generic array of results that is the size of the original list. So this is the results array. This is local to this function. This is a generic array that's local to what we're about to look at. This turns out to be rather complicated to do in Java for a variety of reasons, and this is the way to do it. If you want to make a generic array, this is a way to do it. Completely insane. I don't know why they had to make it quite this hard, but that's what you got to do. So we have an array that's going to hold the results. So we're not actually going to be joining anything together by prepending the elements of the list the way we did with the previous example. Instead, we're going to do everything in place. So here's the splitter task, which we now have as a recursive action because there is no return result. We keep track of the low and the high index in that big array we just looked at. And you can see the constructor initializes low and high. Here's compute. What compute does is it figures out the midpoint by adding the low and the high and dividing by 2, or right shifting by 1. If low equals mid, then we're basically done, and we go ahead and apply the operation from the list onto and then store it in the results array at the right location. Otherwise, it's bigger than 1. And we go ahead and we create a new splitter task, which will be low to mid, and we fork that. And then we go ahead and compute the right-hand side. So this is running in the left-hand side. This is running on the right-hand side. And then we simply join with the result. The only purpose of calling join here is simply to wait until everything's done. We're not actually prepending anything because everything has been done in place in that big results array that we saw, that we allocated through the magic of Java reflection. Here's how we start out. We go ahead and invoke the ForkJoinPool, a new splitter task that goes from 0 to the end of the original list. That's how the wheels start in motion. And then when we're all done, we're now going to go ahead and convert our results array into a results list and return that as the result of the function. And again, depending on various factors, this approach is typically going to be faster than this splitter approach, and that's because we don't have to end up copying the elements, splitting them, and then copying them later. Okay, so the key thing to remember here is that your solution for programming assignment number 4A can be done a variety of ways. You're welcome to use any of these kind of approaches, but you have to use the ForkJoinPool to do all the work, rather than using streams or completable futures. So this will give you some good tips on some good models to use for doing that. And I will put that assignment out shortly.